details, you could then create a formal definition of the Turing machine. You could write out all the transition rules for delta, because they're all here. You know, every state's here. Every transition, every possible transition is marked. Is that true? I need to check that. Okay, a bit of a question mark whether this is complete. I have a query about what happens. Like, remember, for a finite machine, you need as many transition arrows as there are the product of the number of states times the number of symbols in your tape alphabet, I guess. Also a bit of a query. My question mark is this complete? Like for example here, now what are the three symbols? There are three symbols in your tape alphabet. So you need an arrow coming out for all three of the possible symbols that you might be reading on your tape. For a 0, yes. For a blank, yes. And for an X, yes. Actually, this. Oh, by the way, this is shorthand for like 2 arrows. You could have a separate arrow and another state the same, a repeat. So this is shorthand for like 2 arrows. So 3 arrows are coming out of that one. That's correct. How about this one? Blank, 0, X. That's okay. X, 0, blank. That's okay. So it looks as though every case is covered. Every base is covered, as the Americans say. X, 0, X, 0. Oh, blank. Yeah, they're covered. All 3, 0, X, blank. Yeah. Well, there are no transition arrows from halting states, right? So that's normal. So it looks as though it's okay. So it looks as though that diagram is complete. In which case you have a full formal description of the Turing machine. Maybe implicit here, because you haven't written out explicitly the transition rules, but implicitly it's all there. Okay? I mean, you could write out, for every arrow, you could write out something like this. Okay? But that's not been done because it's tedious. All right. Now that's just the formatting in a sense. If you like, it's the statics. But what about the dynamics? Like how, in other words, how does it work? How does it function? Now, for that, you really need to study it. You've got to go into the nitty-gritty details. You've got to ask yourself questions about the high-level design. And flip back and forth between the two. You may ask, okay, well, I think I understand that transition from here to here. Because, and then you ask, you fill in the blanks, the ... Well, why is this transition here? What purpose does it serve in terms of a higher goal? That kind of thing. Right. So let's now talk a bit about. Well, already done it a bit in the previous session, but let's now start interpreting, if you like, the functioning of this state diagram. So how does it start? Well, it starts by, it writes a blank over the leftmost 0 on the tape. Okay, so it's the starting position is here, and it's over. You've got a whole bunch of zeros, sequence of zeros on the tape. Start the leftmost one of those zeros is on the first square of the tape. and the header is positioned, the initial position of the header is over that first 0 at the on the first square. Okay, so the very first thing you do is that you overwrite that first 0 with an X. With an X or a blank? Blank. You put a blank there. And why is that? Well, because eventually, from saying before, you're going to come back. You're going to scan across, from left to right, you'll scan across, crossing, putting X's, oh that's why it's a blank. Yeah. You're putting X's on every second 0, right? And then you'll come back. But how do you know when to stop when you come back? Well, because you've got a blank at that first square. Now that raises another question. I've mentioned this before. I still, for the life of me, not figured out why Sipser insists in starting his discussion on Turing machines with a half-infinite tape. Why not just start with an infinite tape both ways? Other authors do. I've checked. I've looked at what there are lots of textbooks on the Turing machines. It's so basic, and many of them start with infinite both ways, left and right, and that way you wouldn't have to worry about these tricks. So it's a quirk of Sipser, I guess. Anyway, so he starts the discussion on Turing machines with a half-infinite tape. So the left side of the tape, there is a first square, and it extends infinitely to the right. With an infinite number of squares, nearly all of them filled with blanks, except initially your starting sequence, your starting string of symbols, contiguous at the very left. Anyway, so he does have a boundary, a first square on the left. So you then have to bother with all the complications and fringe cases that creates. For example, overwriting the first 0 with a blank, which is here. And the reason you do that is so that, like as I was saying, you scan through the first time and then you reverse come back, and you need to know where the end of your string is. It will be indicated by that blank. Okay. All right. So now another bit of a comment he makes. Now instead of putting a blank there, how about putting a hash sign or a dollar or something else? And well, you could do that and use that as the symbol telling you, oh, you've reached the left-hand end of the string. But he chooses to use a symbol that already exists in the tape alphabet, because then it reduces the size of your state diagram effectively. Okay, so the tape alphabet and the state diagram are kept smaller, and it's already complicated enough. So fair enough. Now, towards the end of the next session, we'll start on the next exercise called exercise 311, and it'll give you a different way to so that you know something you can do, some procedures, some technique that allows you to know that you're at the left-hand end of your tape. Right? Right. Well, what we do now is you've got. We will input a string. Okay, just a minute, I'm getting disturbed. There's kitchen noises coming from the kitchen. I don't know, my brain really needs to concentrate when I'm doing this stuff. I just don't have the luxury of having right brain stuff going on at the same time. I find it hugely destructive and distracting. Anyway, she's Chinese wife. She's gone into her study, closed the door, and things are quiet. Good. All right. So what we're going to do now is we'll do a walkthrough. We will input a particular string that we know will be accepted because it's a power. The number of zeros in the string is a power of 2. You can just see there are 4 zeros here. That's obviously a power of 2. It's 2 to the 2, 2 squared, which is obviously 4. So this string should be accepted by this Turing machine, right? And we will give its history step by step, literally a Turing machine step by step, in the form of a sequence of configurations. Remember we talked about that previous board. So now I'm debating with myself. I have not previously, before when I read things over before I start filming, I was debating with myself, should I go through this in my own head before I start filming? Because it'll take a long time. And there's a lot of little details in each transition, the yielding, the technical term used. One configuration yields the next, and so on. So this one yields that one yields that, and so on. So you have a succession of configurations which give the history of the computation by the Turing machine with this particular input. Now the start configuration, remember the configuration at the beginning, will be, remember the convention? So it will be your start state, and it's to the left of the symbol that the header is on. Well, the header will start at the first 0, so that 0 here is on your first square, the leftmost square. Right? Now we can do it a little bit. So